Hello, everyone. Today we're diving into one of the most fascinating industries in the world, semiconductors manufacturing. How is this tiny chip in your phone made? Why is it so incredibly difficult? And where is this technology headed? We're going to explore the entire journey from sand to silicon, the industry's biggest challenge, and the future of computer engineering. So, for the part one, the chip manufacturing process. So, this reflection. I am Shanaidris Villanueva, by the way. So, all chips start with sand, specifically silicon dioxide, through intense heat and chemical process. Sand become incredibly pure silicon with only one impurity atom per 10 million silicon. This silicon is formed into large cylinders called boules, then sliced into thin wafers that becomes the foundation for the chip. But pure silicon doesn't conduct electricity well. That's why engineers dope it by adding atoms like phosphorus, boron to change its properties. Phosphorus adds electrons, making it n-type conductive, while boron creates electron holes, making it p-type conductive. This enables transistors, the microscopic switches that are the building blocks of all chips. So each transistor has three terminals actually and uses layers of silicon, silicon oxide, or polysilicon. So when voltage is applied, a channel form allowing electricity to flow, the transistor turns on, and then if you remove voltage, it turns off. So billions of these switches create all our computing power. This will happen in clean rooms 10,000, I mean, hundreds of thousand times cleaner than the hospital operating rooms. Workers here wear full bodysuits, can't wear makeup, and enter their airlocks. Why? Because a single dust particle can ruin a single chip. That's so cool, right? Um, for the part two, why chip? Why making chip is so hard? Yeah, why making chip is so hard? So in 1965, Gordon Moore predicted that chip complexity would double every 2 years. This became the Moore's law. It became a self-fulfilling prophecy because everyone believed chips would improve exponentially. They invested exponentially more to make it happen. And today, the industry faces three critical bottlenecks. So, first, instruction set architecture. Only 86 Intel AMD and ARM dominate, and Intel barely licenses 86 and ARM's acquisition by NVIDIA has created access concerns. Second, fabrication. Making chips is so expensive that only a handful of companies can compete. The TSMC, if you're familiar with it, the Taiwanese manufacturer, is worth more than all of Samsung Electronics. They're spending 25 to 28 billions of dollars just on equipment next year. And most competitors simply gave up because costs are astronomical. Third, equipment. Dutch company like ASML is the only maker of extreme ultraviolet lithography machines, essentially for modern chips. So each weighs hundreds of tons and costs $130 million, and only 25 are made yearly. These machines shoot lasers at liquid tin droplets 5,000 times per second to create plasma that generates lights for chip production. So this concentration has massive geopolitical implication. The US cut off Huawei from TSMC by threatening equipment access. Europe is investing billions in chips manufacturing. China desperately wants its own semiconductor industry because they make only 6% of chips they consume despite being the world's electronics hub. And for part three, the photolithography, printing with light. Okay, so the most critical process is photolithography, literally printing with light, invented in 1855. Here's how it works: the silicon wafer is chemically cleaned, then spin coated with photoresist up to 4,800 RPM. A mask, a stencil of chips design, is held above. Intense UV light shines through the mask, causing chemical reaction in the photoresist. Exposed areas are washed away, revealing silicon beneath. And etching chemicals, if you're familiar with it. So etching chemicals, they remove exposed silicon, creating circuit patterns. The process repeats dozens of times, building the three-dimensional chip structure layer by layer. So the key to smaller, more powerful chip is light wavelength. You know what light wavelength, right? So shorter wavelengths create finer details. We've gone from 365 nanometers to much shorter wavelengths today. So today's chips have features at 14 nanometers, which is so far from 365 nanometers, right? Smaller than the most viruses, but we're approaching physical limits where quantum effect cause problem. Sorry for that. So for the part four, the complete manufacturing journey, uh, a wafer's journey takes 2 months. Yeah, did you know that a wafer's journey takes 2 months through hundreds of steps? After photolithography creates transistor structure, dopant atoms are shot into the silicon at high speed through ion implantation. The wafer is heated, causing atoms to settle into fixed position. Given transistors, I mean their electrical properties. Next comes creating interconnects. Trenches are etched, barrier layers applied, then copper is bonded in and excess ground down with micrometer precision. This copper wire can stretch multiple kilometers, all on a fingernail sized chip containing hundreds of billions of transistors. Throughout electron microscopes, constantly monitor every step down to individual atoms. Finally, the wafer is cut into individual chips using ultra-fine saws. Each chip is packaged in protective housing with connection tested and shipped. The result? A finished processor ready to power your device. So, what is the future of computer engineering? Where is this all heading? So, let's explore the key technologies shaping our future as computer engineering uh, student. Quantum computing. So, quantum computing uses qubits instead of bits, processing massive amount of information simultaneously. They can solve problems that would take supercomputers millions of years in seconds. Like, that's so. Okay. Application include cryptography, drug discovery, and climate modeling. AI powered and IoT or Internet of Things and edge computing are game changers. Instead of sending data to distant servers, edge computing processes information where it is generated in your smartwatch, car, factory, and sensors. Combined with all with combined with all the devices with AI, don't just collect data. They learn and adapt autonomously. Next is blockchain. Blockchain is expanding beyond cryptocurrency into supply chains and healthcare. Augmented reality is transforming manufacturing with real time training and retail with virtual try-ons. Cybersecurity. Cybersecurity is critical as everything connects. We're developing quantum encryption, AI driven threat detection, and self healing networks. It's a constant arm race. Every advancement creates new vulnerabilities. Human augmentation. Human augmentation is pushing boundaries. Brain computer interfaces like Neuralink aim to connect minds to computers. Exoskeletons restore mobility where we're not just using technology, we're integrating with it. So, for computer engineering careers, opportunities are exploding. We need chip designers pushing miniaturization limits, fabrication engineers mastering complex manufacturing, software engineers harnessing quantum and AI, cybersecurity experts protecting connected systems, and researchers exploring human computer interaction. The challenge? These fields require interdisciplinary knowledge: physics, chemistry, electrical engineering, computer science, material science. The barrier is high, but the reward is incredible. So, for the conclusion, from sand to silicon, we've seen an incredible journey. The paradox is striking. Massive diversity in chip design exists while manufacturing has consolidated into just a handful of companies. Innovation flourishes creatively while the physical layer requires such extreme capital that monopolies becomes inevitable. We live in an area where hundreds or 100-ton machines shoot lasers at tin to make phones faster, where one Dutch company can determine which countries access cutting edge technology, and where the gap between human intention and machine execution rapidly approaches. What excites or concerns you the most about this future? So you could drop your feedback below. Thanks for watching. Again, this is Shania Dries Villanueva. My reflection for the lectures under microprocessors. Thank you again. Mhm.